And finally, the next things that we did were use machine learning algorithms to label our data as cruising or not cruising, and then finally create a create an aggregated heat map to visualize relative cruising throughout the area. Some of the issues that we had when actually defining cruising was, first off, there is no standard definition of cruising in the literature, and our data was not labeled, so we didn't have any, currently we did not have any ground truth. Our solution was to use a multi-step classification approach, label a subset of our extreme cases as cruising or not cruising, and also use machine learning to identify cruising indicators. Fred will proceed.
So one of the first things that we wanted to do was label the data. And by this we didn't have really a standard way to label cruising or not cruising. And if we label these extreme subsets, we could hopefully find a machine learning algorithm that can detect the rest. And so we use something called a distance ratio. And here you can see in red a typical path that someone might take. And outlined in blue is the shortest path from the start point to the end point of that. So in this case, the total path divided by the shortest path is 1, which is a relatively low distance ratio. On the other hand, this is a start to end path where there's a lot of nodes traversed. However, the shortest path is only really touching 2 nodes. And so with that, you have a high distance ratio. So we use this sort of algorithm to label the extreme cases of cruising or not cruising, develop a machine learning algorithm that could sort of go off of that, and then label the rest of the data with that as well. And so we ended up with all these paths that were considered cruising throughout downtown Seattle. And so next step we took was aggregation. And so the path 1 traversed A, B, C, and D, path 2 was B to C, and path 3 was B, C, and D. And so just specifically, we looked at how many people traveled between each node, and were able to aggregate that. So between A and B, there's only 1 person that was cruising. Between B and C, there was 3, and between C and D, there were 2. So with that, we were able to develop a tool for the downtown Seattle individuals to use. So if you were looking at what parking on a Monday morning looked like, you're able to get a real-time view of what this actually looked like in downtown Seattle. And what this is able to do is sort of provide better information with that. So the downtown Seattle area can now better optimize parking rates that are going on. They can have better observations of and include more signage to direct people to parking when they need it. Another opportunity as well is to sort of have this as a published data stream that someone like Google picks up, and when they're able to look at these aggregated counts of where people are traveling in high traffic areas, they're able to route people around those as well. All in all, this can also be applied to other cities. We focus on reproducibility and documentation throughout the process to really make sure this is a key component of that. With that, we'd like to thank the following sponsors. It was an amazing summer, and we had some really great support with that. We have an additional 60 slides appendix if anyone wants to hit some afterwards. We'd love to talk you through it all. But yeah, that's what we did. Thanks.
The next presentation is Mayuree and Jacob Rich.
Hey guys, I'm Jacob. Thank you so much for having us. I'm going to represent the Data Science for Urban Equity. We were a Data Science for Social Good team from Seattle. And so our topic is exploring gentrification and hoping to build a suite, a feature that allows policymakers to better understand how to use data that can be very complex to make decisions that have ripple effects throughout the entire city. So I'd like to talk a little bit first about I don't know how to use the technology. Sorry. There we go. I got it. I figured it out. Sorry. So I want to talk a little bit about why the Seattle metro area. It's a model city. It's a city that works well in a petri dish. It's seen explosive growth over the last 10 years, as well as unequal distribution of that growth. So there's all these issues that crop up around equity and about the distribution of growth within Seattle. So we decided we wanted to study it and really use it so that we could draw some conclusions about how to model things. So our project output in the first 10 weeks. So we built a visual interactive tool, and we built a structural equation model to understand the underlying structures within the data. Now behind all of this was a comprehensive literature review in which we made sure to study and understand the variables we were putting into the model and granted that they were valid as well as used ethically. So current practice in the field regarding mapping of opportunity and equity. A lot of it occurs in the city scale, and interventions tend to be far more localized, although without consideration of the other localities nearby. Usually single variables are demonstrated, or they use indices of equally weighted variables to combine and understand something, say, urban equity. Someone would build an index for that. Here's what our visual tool looks like. As you can see on the left, you can select your variables. And on the right, we have a description of some more interesting facts, as well as a histogram that lets you understand where that specific neighborhood, census tract, or block group falls within the greater scheme of Seattle. Now, you can zoom in to tract level, so the previous one was at the neighborhood level, and then you can go to a deeper granularity at the census tract level, and one step further to the block group level. We decided to include this feature because having the ability to see the whole picture, but also having the feature to zoom in is a powerful tool that we think makes it much easier to interact with this data. You can actually zoom in even further to the actual local level to see things such as hospitals, schools, parks, recreation areas. And we continue to add to this because we think that this would be the most powerful component that we could develop for this actual visualization tool. Oh, and the last thing I want to point out is that right down here we have our model prediction tool. That tool allows you to select a specific block group and then select a specific variable. And using that variable, you can change the value and see what it does to our structural equation model themes that I will touch on in a moment. So, when we thought about the model, we obviously thought about some of the other ways in which people modeled urban equity. Things where you take multiple variables, you take your dependents, you take your independent variables and use them to predict your dependent variables. We wanted to try something different because we wanted to make it so that our model would be useful to facilitate applied research into this. It would be useful for policymakers and it would be useful for other stakeholders within Seattle. So, as I said, dependent variable predicted using the independent structures. We wanted to try something different. It's very difficult to get a grasp on what actually urban equity is. How do you measure that? What are your values for that? So we turned it into a structural equation model where you create themes, and through a process of principal component analysis and factor analysis, you're able to create these themes. And through that literature review, we're better able to understand what variables need to go into each theme. And using those themes, we then create our structural equation model. This is what our model looks like as of right now, where you have these large themes that manifest themselves in the other variables. And it shows the structures that lie beneath them, hopefully allowing us to better understand the ways in which development and equity work within a city. So as you can see, socioeconomic well-being relates to connectivity, relates to development. That's something that we might expect to see, and it's also a powerful thing that we might expect to see. That creating connectivity can also boost the development that occurs. So our next steps are private beta for our website and model enhancements. And if you're interested, you can always come talk to us. We want to thank our sponsors really quickly. This is us, and I want to just say a huge thank you all for listening, for allowing us to come and talk. And if you want to talk further about this project, please come find me or Hillary. We'll both be here. Thank you.
Next is Mayuree, Binjolkar, and Andrea, also from DSSG 7.
Hi everyone, I am Mayuree and this is Andrea. And we were DSSG fellows at the UW this summer. And we worked on improving urban mobility using electronic smart card data. So nowadays, a lot of transit and transportation-related data is available, and this data can be used to actually improve the transit performance or the transportation performance, but this data needs to be converted into useful information so that we can get those kind of insights into our data. And we basically use the electronic smart card data from the Orca card, which is basically the electronic smart card used in the Puget Sound region in Washington state. And this data basically consists of transaction information, which is like the date, the time, and the information about the bus route on which the transaction was made. And this data alone is not very useful because it's not geolocated. So then we took data from 6 different transit agencies, and basically we had a huge amount of unclean Orca data and a lot of unclean GPS data, which is basically the automatic recalculation data, and we had a very bad origin-destination estimation for the entire Puget Sound region. So our project basically was about improving this origin-destination estimation for the Puget Sound region and basically giving deeper insights into the travel patterns in that area. So I'm going to start with an example of the University District area in Seattle, which is basically the area around University of Washington. And a light rail station was added in 2016 to the near University of Washington. And we have the data sets from 2015 and 16. And we saw a 57% increase in the total number of boardings. But 50%, or even actually more than 50% of these boardings are actually transfers, by which I mean people get down from the first bus, and they have a 2-hour time window to get on the second bus and not pay for the second ride. And when we look deeper into that, we saw that those transfer records, half of them are actually not transfers. So I'm going to give an example about that. People usually go to the intramural activity center, which is basically to exercise there and then hop back on the bus and use that 2-hour time window to actually do an activity and not really use it as a legit transfer. And we wanted to separate out these fake and real transfers so that we could have cleaner origin-destination estimation. So we took the transfer data and we just defined the real and financial transfers to get a better understanding of the origin and destination. We started building models. We started with the Gaussian mixture model, which didn't work out at all. And then we had a huge amount of unlabeled data. We had a very small amount of labeled data, so we used semi-supervised learning-based model. And we actually got pretty good results because here's a map of the University District area, and we found that near the light rail station is here, a lot of real transfers are happening and people are not actually doing any activities. But near the shopping complex and near the student union building, people are actually just grabbing food or something, and actually a lot of fake or financial transfers are happening there. Also, we had a lot of other biases in our data set, which need to be removed because these biases actually can be existing in any sort of traffic and transportation data, and Andrew's going to talk about it.
Right, so as Mayuree mentioned, the second component of our work this summer was the bias analysis, or accounting for the fact that we have Orca data, which is potentially very powerful and informative about transit ridership behavior, but we also know that it has a serious limitation of bias, which is that it only captures Orca users. Now we know that Orca users make up about 70% of the total ridership behavior, or I'm sorry, total ridership population, but this ratio of total passengers to the number of Orca passengers varies quite a bit between individual bus boardings. And just as an example, you can see a map of King County that's divided into various geographic zones. And the color shows the corresponding average percentage of users that did not use Orca. So in other words, it just shows all the passengers that aren't included in our data set. And this varies quite a bit by geography, but this map doesn't even capture time, bus routes, and all these other factors that go into the ratio between Orca passengers and the total number of passengers. We're lucky, though, that we have a separate orthogonal data source, which is the automatic passenger count data, that does capture the total number of passengers. And this is just a sensor that's on some buses, and this counts the number of people that board a bus, regardless of how they pay, whether it be cash or with electronic or smart card. So we have far fewer data for these trips, but we have enough that we can combine the data sets and make a model that can understand or predict the total number of passengers given the data we have. And the approach we chose was a zero inflated negative binomial model. And we chose this for a couple reasons. The first is that it's a regression, which is simple, but it's very interpretable, and would give us a clear understanding of what affects this total number of passengers. When you're working with count data like this, standard approach is just to use a Poisson distribution, but we added a couple extensions just to account for or accommodate some quirks in our data. Specifically, it's very over-dispersed, so we chose a negative binomial distribution, and we have an excessive number of zero counts, which is partly due to the fact that there are a lot of bus points where nobody actually gets on, but there's also a lot of noise in our data. Our final result is a series of models that perform, depending on the route, about 30 to 80% better than what we had before. And with these models, we should have a much better understanding of what transit ridership is in Seattle based on the data we have. This is a work in progress, though, and we have a couple projects that are in some phase of progress. The first is just kind of deploying our models across the data sets we have and across future trips. We're also working on hidden Markov models and neural nets just to account for some of the things we couldn't find. And we'll be around, so if you guys have any questions, please feel free to talk to us. Thank you.
Next is Matthew Cooper, also from DSSG Seattle.
Hi everybody, I'm going to tell you about one of the projects at DSSG Seattle called Vital Signs. Vital Signs is a program within Conservation International. It's a monitoring system designed to collect data across 25 landscapes in 4 African countries, Ghana, Rwanda, Tanzania, and Uganda. And Vital Signs collects data on human well-being, the environment, and agriculture. And the idea is to fill data gaps and inform policymakers so they can better understand how to support human well-being via the environment, how people's livelihoods and agricultural systems in Africa depend on ecosystem services, and also make sure human development and agricultural intensification don't degrade the environmental services that everyone depends on. So here's sort of a simplified schema of the data we collected. For households, we conducted surveys, asked people all about their sort of household economy, income, assets, events and shocks, demographic data about all the individuals, education levels. For every household, we asked about their fields, collected soil analysis in their fields, looked at crop yields, inputs, farming practices. And finally, near these households and fields, we collected environmental data on land cover, again, soil health, and the idea was to have a data set of human outcomes and environmental outcomes co-located in the same places. So we could really look at these landscapes as sort of a social ecological system and better understand interdependencies between these variables. So one of the analyses our team did this summer looked at water scarcity in the dry season. So here you can see daily per capita water use. When you look at this compared to WHO recommendations, many of the households are not getting adequate enough water. And so, so it's really critical to better understand where people don't have enough water, to get more information to look at how long an 8-minute shower would take.
Okay. So our goal was to build a model using the random forest approach, where we predict monthly water insecurity reported by the Vital Signs households using geographic data and watershed characteristics. So some of our variables were elevation, travel distance, demographics, climate, and then proportion of forest, cropland, protected area, and degraded land. And we took this model and extrapolated it out to the entire country for all 4 of our Vital Signs countries. And with this, we created an interactive map, which we'll link to at the end. But with this map, users can look at which areas are more likely to experience an event where they don't have enough water, and like in which months this would happen. We're also interested in improving our model performance by including socioeconomic data in addition to the geographic data and watershed characteristics. So we included household surveys from the vital signs data in our model. Some of the more important variables we found were household size, water use, agricultural production, and wage labor income. And with this, we made predictions just about the vital signs household, so this one is not extrapolated. And overall, we found better model performance. For us, what was most important is that we were making predictions that were more accurate with true positives. So are we predicting a water insecurity event when there actually is one? But overall, across many indicators, we found better performance when we included these socioeconomic variables. So this is an example of how including interdisciplinary data can be useful for solving complex problems. And then finally, we'd like to thank our funding sources. And if you're interested in looking at our interactive map, you can go to dssg.resilienceatlas.org. And if you're interested in more analyses that we completed over the summer, you can go to vitalscience.org/blogs, and you'll see blog posts about past analyses and ongoing analyses.
Next is from DSSG ITAM, Jonathan Galsurkar.
Thank you, everyone. So I was part of data science culture at IBM, and our project was semantic searching for efficient assessment of first-signal development. And so our partners are the UNDP, United Nations Development Program, and what they do is they help countries implement the UN Sustainable Development Goals, which tackle major societal problems such as poverty, hunger, and environmental degradation. And there's actually 169 targets of these goals, which are more specific plans of action must be completed for the goals we met. And so the first step of helping countries implement these goals is actually called the Rapid Integrated Assessment Methodology. So policy experts from the UN will actually read all the national plans from the country and find specific sentences or paragraphs that match one or more of the targets of the 17 Sustainable Development Goals. And although this is called rapid, there's actually hundreds, about thousands of pages for them to read, and this takes about 3 to 4 weeks currently, and really requires a domain knowledge that only policy experts have. So with IBM, we decided to apply natural language processing techniques, specifically sentence embedding and semantic search techniques to actually automate the RIA. And we chose embedding techniques over general back-of-words models because, as you can imagine, there are many different ways to actually write policy documents with many different words. But we won't be able to actually capture the semantics if we just look at the words individually. So embedding techniques allow us to provide a numeric representation of an entire sentence or paragraph, which captures its actual meaning. And so to do our sentence embedding, we first use a tool called Word2Vec, which can provide very powerful word embeddings. And then using the word embeddings, scaled by some kind of scaling factor, we found that the TF-IDF score of the word is pretty good. And we sum them all together for all the words in a sentence, and now we can embed in a sentence or an entire paragraph, which will capture the actual meaning and semantics of that entire sentence or paragraph. So our general methodology was like this. First, we learned the embedding space. So what do we have? We have the target description. So what does that actually mean? By 2030, let's try to find out, or let's try to end all job scarcity in certain countries, so on and so forth. And we take all that, as well as all the sentences that were found in previous RIAs that match that target. So we concatenate all those sentences, embedded them, and that's in our embedding space. Then for every single sentence in the policy document, we do the same kind of embedding, find its cosine similarities to each of the targets, and at the end of all that, sort by the target all the closest sentences to it, provide that to the UNDP, and then after that, policy can evaluate our results. And those evaluations should be incorporated in future models by concatenating more of those sentences to the target description. And our only way to really compare our results is to look at the RIAs that were already conducted and see how many matches we get with them. And so, of course, as we show more sentences, we can get a 100% match, but ideally they want only about 30 sentences. So depending on the country, we get between 15 and 50% matches. And actually what's interesting is that they confirmed that this represents exactly how hard it was for the UNDP to conduct the RIA themselves manually. And of course, that number was really an average across all targets. Per target, it really varies. Some targets, after seeing 5 sentences, we can get all the matches they had, whereas others, even after 100, you can get 1 match. But it's good to note that although we can't get all the matches they found currently, we found many matches, which are here in bold and starting from them, that they didn't find when they conducted their own RIA, that they agree should have been actually part of the RIA themselves. And finally, the whole point of this is to make their process a lot faster. So we conducted a pilot study with Papua New Guinea. Their RIA was not actually conducted previously. And with 17 policy documents on 1,500 pages for them to read, they estimated it would take them a few weeks to complete and they didn't have the time. So within an hour, I was able to give them a RIA with high quality matches. They agreed that the targets were very relevant, and the matches were in fact very applaudable. And they estimate the time they complete now a RIA will take about 3 days at most, instead of 3 to 4 weeks, because the evaluation results only takes about 1 to 2 days, and if they have 2 UNDP policy experts, it'll take even possibly 1 day. And further research includes exploring various scaling factors, creating larger scale studies, because the more RIAs that are conducted by our system, the better our results, because we'll have more training data for the word-to-vec model, as well as more sentences that append to our actual embedding scheme, and of course, proper filtering results. And this is my mentors, and thank you very much.
Next is Timothy Megam, also for DSSG ITAM.
I think it's Adi. Oh, no worries. I'm the next one. Don't worry.
Oh, sorry, it's Aditya. Sorry.
Thank you. Hello, everyone. I was part of the IBM Social Good Fellowship Program over the summer. And what we did there was we worked with this organization called Echoing Green, which is a social innovation fund which fosters social good by promoting entrepreneurial ventures in the social domain. How to do this is using through their fellowship program, in which they provide ventures some seed funding, a leadership program, and a community of mentors and experts. But to select these fellows, they take them through a rigorous 4-stage selection process, which involves screening 3,000 online applications manually, which are finally, in the first stage, out of these 3,000 applications, they reject around 85% of these applications to select 500 semifinalists. Out of these semifinalists, these applications are again reviewed at least 20 times by evaluators to come up with 60 finalists and finally end up with 30 fellows. As you can imagine, this entire process takes a lot of time. It's pretty resource intensive and is relatively subjective. So what IBM did with this organization, we partnered with them to take a data-driven approach to selecting and finding the ideal fellow and help them answer these 3 key questions. So the questions that we were looking to answer were, can we identify defining characteristic traits of an ideal social good fellow? Can we identify any unknown biases in the application process? And if it's possible, can we introduce some automation to the process so that we can achieve this whole process make it more efficient? So how we went about it, I'll just take a very brief approach to our overall methodology. First step involved integrating data across five different years of applications. So as you can imagine, the data across different years across application was not very structured. So once you combine data across 5 years, which was in the form of application questions that applicants answer about themselves, their problem areas, the idea that they're proposing, and the organization that they are building. So the major aspect of our project was extracting as much information as we can from the free text data that the user entered. So that involved natural language processing techniques through which we extracted features like specific themes or topics that an applicant talks about, which involve unsupervised topic modeling. The next thing we extracted was syntactic features, which defined the way the applicant actually writes his application. Third thing was lexical features, which denoted the words and vocabulary used by the applicant in his application. And the fourth was using IBM Watson API to extract personality features out of raw text data. And finally, using all these features that we extracted from free text, we built a classification model to predict the probability of an application making it through the process. So once these features were engineered, we studied the distribution across different application stages. And some of the interesting results that we found out were these. So when we looked at themes and the distributions across different application stages, we found that applicants who talk about social impact and their background in technology, applicants who talk about their idea being about an online platform or data related, or people who are addressing problem areas with measurable impact tend to be more successful than applicants who do not. Whereas, as expected, applicants who talk about not concrete examples but talk about vague text tend to be less successful as compared to others. So this was related to what the applicant talks about in his application, but how the applicant talks about these topics in the application was also important. So when we studied the syntactic features, we found that applicants who are more detailed in describing their ideas and solutions tend to be more successful. Applicants who use more number of uppercase words, which could relate to the organizations that they're working with or describing their educational background, also tend to be more successful. Applicants presenting their idea in a unique way, using specific novel words or sentence structure, tend to be more successful. However, readability, which is the measure of difficulty of the language used, did not seem to have any effect on the application success, which was kind of a favorable outcome that we were looking for. Next is the important part because Echoing Green values the applicant more than the application itself. So we wanted to study if there are certain personality traits that favor your application. So as you would expect, we found that applicants who show traits of immoderation or overindulgence tend to be less successful. Applicants who show self-discipline tend to be clearly more successful. But the surprising results that we found were related to neuroticism and openness to change. So successful applicants tended to have a higher score in neuroticism, which we hypothesize is because neuroticism could be indicative of your passion towards your idea. And that's why you could see that applicants would have higher score in neuroticism, had a better tendency to be successful. Whereas compared to openness to change, could be a measure of your irresolution towards your idea, and that is why it could be seen as a negative trait in an applicant. So we also found some other informative features that we found were the funds raised by an applicant before applying to the fellowship were clearly indicative of your resource magnetism that favored your application. Next was if you're a reapplicant or have a website, you're twice as more likely to be accepted for the fellowship compared to an applicant who doesn't have one. And finally, the younger you are, it definitely makes your application more favorable. So once all these features were extracted, we use these features to build an automatic classifier. And we train a classifier using these features and assign a probability score to each application so that we can predict its probability of making it through the application process. And by choosing an appropriate threshold, we could successfully reject almost 61% of the rejected applications. So in the entire process, 85% of the applications are rejected in the first phase, but we were able to reject 61% of them while minimizing our false positives, which is not rejecting people who were qualified but didn't make it to the application. So we don't want to use a system as a yes and no system, rather as a prescriptive system for the organization, which they can use to allocate their resources in an optimized manner. So in conclusion, if any of you wish to apply to any social entrepreneurship venture fund or fellowship application, things to keep in mind. For a successful application, an applicant should talk about his experience with social impact organizations, talk about his technological background, and try to cite concrete examples and not be vague. Should preferably propose an idea, a data-based idea which has an online platform, and should target an area with measurable social impact. Should write about it in as much detail as possible and present it in a novel way. Should exhibit traits of self-discipline, show his passion, and not allowed to sound immoderate or irresolute. And should ideally raise funds and definitely have a website. So that's all from me and our team. So I thank everyone at IBM Research and Echoing Green.
Next is Timothy McCampbell from DSSG ITAM.
IBM fellow with DSSG. I'm also a student at the University of Michigan, and today I'm going to be talking about our Cognitive Disease Hunter project, where we developed an automated pathogen feature extractor from scientific literature. Okay, so this is my team. So I was lucky to be mentored by a lot of wonderful people at IBM, and we were partnering with the Cara Institute, which is a nonprofit biological research institute in New York. So first, what are we going to be talking about here? We're going to be talking about zoonotic diseases. So what are zoonotic diseases? They are diseases that can spread from animals to humans, either through direct contact, indirect contact, either through mosquitoes or other vectors or food. Why are they important? They're important because basically a majority of new and emerging infectious diseases are zoonotic. And some of the major epidemics of the last 50 years have all been caused from zoonotic diseases. And examples like those listed up here, so Zika, Ebola, HIV, influenza, etc., are all zoonotic diseases. So there's this question, and it's kind of been a theme, I guess, here at this conference of, can we maybe predict the next zoonotic disease and then take a more proactive approach to disease control as opposed to a reactive approach? So that's kind of the goal. We could help mitigate the disease before it even starts becoming an epidemic. So if we did that, it would be pretty standard prediction. We have our database of pathogens and all their different features. We develop some models that can do the prediction, finds the most predictive features that predict whether or not it is zoonotic, and then you give me a new pathogen, I say, oh, it has these features, we think it is zoonotic, or we don't think it is. So that would be nice if we had that pathogen database, but unfortunately that database doesn't exist, so we can't do this prediction. So kind of the goal of this project is to extract that information from academic journals. So these pathogens and their features are known, they're written about in academic papers, and we want to do that feature extraction automatically and create that database so we can eventually do the prediction. So that was kind of the goal of the summer. So how are we going to do that? So how are we going to actually get this database and extract those features automatically? We're going to take an ontological learning approach, which is basically 3 steps. First, you create a type system, which kind of defines what information you're interested in from these academic papers. And then once you have that type system, you have humans come in and annotate those documents. So they basically show how to identify that information in the documents. And then with that training data that you've gotten, you can develop an automated annotator that can read in any document and basically annotate it for you based on that type system. Just going in, so here's a quick example. So it says chikungunya virus is a mosquito-transmitted alpha virus. That would be a sentence in an academic paper, and our goal would be to label the different types, like disease infectious organism and transmission features, and their relations automatically. So we want to get that labeling automatically. Just cool. So just going into a little bit more detail. So a type system has 2 things. It has entities and relations. Entities are classes of words or short phrases, so like disease infectious organism, capsid structure, transmission feature, and then relations are basically how these different entities relate to each other. So we had to develop this type system first for our application of interest. And then once we have that type system, we basically have humans come in and annotate documents based off of that type system. And we need about 300 human annotated documents. Once we get those annotated documents, we can learn a model that learns based off of these human annotations how to do this automatically. So just this quick graphic, if we have 300, we can learn the model based off of the 300 how to identify these entities and relations automatically. And then once we have that model, we can basically feed in a corpus of academic literature, and it'll do all of the annotation automatically for us. So that's the goal. Where are we right now? So we have the type system fully developed, but we're currently in need of more training data. Like I said, we need 300 human annotated documents, so we're in the process of training new annotators to do this to get this training data for us. Based off of our small amount of training data, we are getting pretty good results, which is a sign that our type system and annotations are on the right track. And so future work includes, like I said, getting more annotations, like training data and training new annotators. And then once we fit the model, it'll be this iterative process of improving our type system, improving the annotations, and then fitting it again until eventually, we're getting the features out of that academic literature and then using those features to predict the next zoonotic disease. So everything. Thank you so much.
And our last presentation for this session is DSSG Taiwan, Yayushen.
Hi everyone, I'm Aditya, and I'm a data scientist in this group. Today I want to show you about our case study of building an effective public-private partnership on domestic violence prevention. We'll call it DV in my presentation. Why we set up a PPP is because traditional in my country we use the AMI approach or the government outsourced approach to deal with DV prevention, but it failed to hit the pain point of social worker. So this PPP is more successful. I will show you our results. This program is conducted by DSSG. They have a social good initiative, and since 2016, we have more than 50 volunteer data scientists in our team and complete 9 projects. And today I will show you about our DV risk management. The high impact of our project is, as you can see in the screen, we successfully increased social worker professional stakeholder literacy. She is the director of the Taipei City DV prevention, and she has visited a lot of workshops to introduce our results and successfully increase the literacy. And also, our result implement differentiation prevention strategy to achieve a village and distance. And with our, we have extended projects include to predict high-risk families and optimize the call center workflow. The reason why DV is an issue in Taiwan is this data is in Taipei City. We can see from 2009 to 2015, the reported cases are increased at least 20%. And a social worker should handle 116 cases in a single year. It's a heavy workload. Among these cases, 50% are intimate partner violence cases and 33% are repeated victimization. And with this data, we know we can set up 2 different strategies for our program. The first one is community level, and the second one is individual level. In community level, we have this screenshot. You can see we have this map to show the user. The user includes government agency or the frontline social worker. They can see the distributions of the case reports and their rank among of other area. Okay. And today we are focused on the individual level. We built a prediction model for links. This we ran a long time for risk factor selections. You can see in the circle, there are 3 different categories of the data: individual, relationship, and community. And out of the circle is our corresponding variable in our database. This is a partial result of our random forest model. Something interesting in it, this data tells us something is different from our common sense. You can see the top of this tree, disability or mental illness. Common sense tells us that someone who suffers from disability or mental illness will suffer from worse cases, but this data tells us not sure. You are not sure about not sure about your case of disability or mental illness, or you don't know. It's a high risk. You will leave the case in a high risk. In the right side of this screen, the yellow number shows the higher prediction numbers of our model. Our performance is really great. You can see the accuracy is higher than 96%, and the recall rate also high. Recall rate is really important in today's case because we don't want to miss any potential big repeated cases in our project. So we need a higher recall rate. Okay. And how to use our models? We are going to a system for the social worker. When a case first comes, they can type some information of the cases in this system. And a prediction model will intensively give them the risk level, high, medium, and low. And they can set a different strategy with the case has different risk level. And also, this model can increase the case's self-awareness because in this tree you can know that if the case is not sure what the state of mental or physical, they are in danger. So increase the self-awareness is another important issue in today's case. Okay, this is our team members, and that's for everyone's contributions. And if you are interested in our project, you can visit our website info@sg.org or connect with us. Thank you so much.
Thank you. I have two announcements to make. The launch time would be in specific table topics. A few of them is going to be from people who did lightning talks today. Another one from Jerica Coverley from Civic Data Scientist at Evansville Vanderbilt Public Library. And she will be talking about how to build a community of data scientists as a solo data scientist. And Anissa Tanweer from the University of Washington interviewing some DSSG alumni. And also the workshops start at 1:15 p.m. and some of the workshops are in the center floors. So you have to go down, take the elevator to the 3rd floor and then take the elevator up to the 22nd floor. So take your time to do that. So see you later. Thank you.